Welcome back to Introduction to Higher Mathematics. In our last lecture, we delved into the topology of the real numbers. We started by defining the notion of a metric, that is, a distance function that must be positive, definite, and symmetric, and satisfies the triangle inequality. A set that's equipped with such a metric is often called a metric space. We briefly talked about the Euclidean metric, the most common one we use, which is a generalization of the distance formula you learned in grade school. From there, we expanded our terminology regarding sets, beginning with the concept of a neighborhood, the set of all points less than but not equal to some distance away from a point. We saw that sets can be open, meaning that all points have neighborhoods contained completely within the set, or they can be closed, meaning that their complements are open. These aren't the only two possibilities, though, since some sets can be neither open nor closed, and some sets can even be both open and closed, in which case we call them clopen. Next, we broke our sets into three parts: the interior, the exterior, and the boundary, all of which are rather intuitive concepts, but which we define in a formal mathematical way. We saw that sets could be connected or disconnected, or even totally disconnected. We said a set was disconnected if we could split it apart using open sets. We focused on cluster points, around which there are an infinite number of points from the set in question, even though the cluster point itself need not be in the set. Finally, we examined the Cantor set, a truly bizarre set that seems to be nothing but dust, yet somehow contains an uncountably infinite number of points. In continuing our study of the real numbers, it's time to turn in a slightly different direction. Rather than looking at the nebulous open and closed sets at once, instead we're going to look at the individual points in these sets, put them in order, and see where they go. In other words, it's time to look at sequences. A sequence is an ordered list of elements taken from some set. We often call the particular items in the list terms of the sequence. So as a sequence is ordered, it has a first term, a second term, a third term, and so on. In fact, something about this, putting things in order, should sound quite familiar to you, given the things we've been discussing. When we say that these terms have an order to them, what we mean is that they can be put into one-to-one correspondence with the natural numbers. So in essence, a sequence can be thought of as a function for which the domain is the natural numbers and the codomain is the set from which we're pulling the terms of the sequence. So really, we were already dealing with sequences when we were trying to prove that sets, such as the even numbers, the integers, and the rational numbers, were countable. What we were trying to do was find a sequence that would eventually be guaranteed to touch on every member of the set. So even though sequences are quite familiar to us by now, rather than just using them, at this point we're going to look a bit more at the sequences themselves and their properties. So first, let's develop some proper notation for sequences. We can't use the curly braces like we do for sets, since sets are generally not ordered. And we shouldn't use parentheses like we do for tuples, because even though tuples are ordered, they usually aren't supposed to be infinite. So instead, we use these angular brackets to notate sequences. We can use them in two ways. First of all, we can actually list the terms of the sequence in order, separated by commas. This is useful, but remember the trap that we can fall into anytime we have a ... after enumerating a pattern. There's always the possibility that the sequence we think we have is in fact not the correct sequence at all. So the second possibility, which is a good bit more unambiguous, is to simply put the rule for the nth term, so the function, between those angle brackets. Usually, just to show that this one thing in brackets is a rule that's supposed to apply to all natural numbers, we'll put the fact that n should range from 1 to infinity on the right. And as you've already seen from working with index sets, we usually index our terms of the sequence using subscripts. So a sub 1 is the first term, a sub 2 is the second term, and in general, a sub n is the nth term. Let's look at a quick example. Say we have the sequence n squared from 1 to infinity. The individual terms would then just be what we get by successively plugging in the natural numbers starting at 1. We would get 1, 4, 9, 16, 25, and so on. So the nth term is the nth perfect square. Really, notating sequences is pretty easy. So this is all the time we really need to spend on it. When we're working with sequences of real numbers, we often display sequences by using a graph, just like the XY graphs you're used to. On these graphs, the horizontal axis represents which term we're looking at, in other words, natural numbers, and the vertical axis represents the value of the term we're looking at. Then we just place a point for each term of the sequence. Be careful if you do this not to connect the dots. The domain of the underlying function of a sequence is always the natural numbers. After all, it makes no sense to say what the 3.4th term of a sequence is, does it? So now let's look at some of the properties of various sequences. The first thing we might observe when we look at a sequence at a glance is the general direction in which the terms are progressing. Are they getting larger? Are they getting smaller? So, as you might have guessed, we need to make some new definitions so we can describe what we find. An increasing sequence is one for which a sub n plus 1 is greater than or equal to a sub n for all natural numbers n. In other words, each term is always the same as or larger than the one before it, even though just how much larger it is may change. Sometimes we might want to restrict things just a little bit more and require that each term be strictly greater than the term before it, never equal. In this case, we might call such a sequence strictly increasing. So for instance, the sequence 1, 1, 2, 2, 3, 3, 4, 4, and so on is increasing, though it's not strictly increasing. Now there's a few corollaries of this definition. First of all, there are two numerical ways to show that a sequence is increasing, both of which come from algebraic manipulation of the inequality. First of all, we could subtract the nth term of the sequence from both sides, which shows us that a function is increasing if and only if the n plus first term minus the nth term is greater than or equal to 0. In other words, each term minus the one before it is positive or 0. Second of all, if we know ahead of time that our terms are all positive, never negative or 0, then instead of subtracting the nth term from both sides, we could divide both sides by that nth term, which leads us to another observation. A sequence is increasing if and only if the n plus first term divided by the nth term is greater than or equal to 1. In other words, the ratio of each term to one before it is at least 1. Another observation we might make about increasing sequences is that not only is each term greater than or equal to the one before it, but it's greater than or equal to every term before it. In other words, a function is increasing if and only if the mth term is greater than or equal to the nth term whenever m is greater than n. This is true because order relations are transitive. Remember that if a is greater than b and b is greater than c, then a is greater than c. So all we need to do is chain a bunch of adjacent inequalities together and let the transitive property take over. In the same way that a sequence can be increasing, it can just as easily be decreasing. A decreasing sequence, as you might expect, is a sequence for which a sub n plus 1 is less than or equal to a sub n for all natural numbers n. In other words, each term is always the same as or smaller than the one before it. Then, a strictly decreasing sequence is one for which each term must be strictly less than the one before it, again removing the possibility of equality. So, for example, the sequence 1, 1 half, 1 half, 1/3, 1/3, 1/3, 1/4, 1/4, 1/4, 1/4, and so on is decreasing, though it is not strictly decreasing because some of the terms are repeated. The corollaries work equally well for decreasing sequences as well. A sequence can be shown as decreasing if the difference between a term and the one before it is negative or 0, or if the ratio of each term to the one before it is less than or equal to 1, provided, of course, that the sequence is entirely positive. And, of course, If its sequence is decreasing, it means that each term is less than or equal to every term that comes before it, again by the transitive property. Now, we can take these two concepts, increasing sequences and decreasing sequences, and unify them into a single term. A monotonic sequence is a sequence that preserves the same order relation between successive terms. So, a monotonic sequence must be either increasing the entire time or decreasing the entire time. Or, of course, it could stay constant, in which case it could be viewed as either increasing or decreasing. But that wouldn't be a particularly interesting sequence at all. Not only that, but a strictly monotonic sequence is one that preserves a strict order relation throughout. In other words, it's either strictly increasing or strictly decreasing. But why bother making up a new word if all it means is increasing or decreasing? Well, increasing sequences and decreasing sequences have a number of useful properties. In fact, they have pretty much the same useful properties, just in opposite directions. So it makes sense to unify them because of how similar they are, and then concentrate on the details later. Or perhaps it's because textbook writers don't want to write everything down twice, once for increasing sequences and once more for decreasing sequences. Some would call that laziness. Others would call it efficiency. Take that as you will, I suppose. Anyway, here's one rather nice property of monotonic sequences. If a sequence is strictly monotonic, then the function from the natural numbers to the given set is guaranteed to be injective or one-to-one. Basically, since the terms of the sequence are either always getting larger or always getting smaller, no two can ever be the same. The sequence can't pause because it's strictly monotonic, and it surely can't reverse direction. So that's enough about monotonic sequences for now. Next, let's look at a different property of sequences: boundedness. We want to know, will the terms of a sequence be restricted to a certain range? To begin with, we say that a sequence is bounded above if there exists some number big M, such that every term a sub n of the sequence is less than or equal to big M. In other words, the terms never get any bigger than some particular number, which here we're calling big M. We would then call this big M an upper bound of the sequence. Hey, that sounds familiar too, doesn't it? We already talked about upper bounds a bit when we constructed the real numbers out of Dedekind cuts. The idea here is much the same. A sequence is bounded above if the set of all terms has an upper bound. As I'm sure you've already anticipated, we can say that a sequence is bounded below if there exists some number little m, such that every term a sub n of the sequence is greater than or equal to little m. In other words, the terms never get any smaller than some particular number, which here we're calling little m. Again, as I'm sure you've already deduced, the number little m would be called a lower bound of the sequence. We can also reverse these two definitions and talk about what it means to be unbounded above or below. A sequence is unbounded above if, for any big M we choose, no matter how large, we can find a natural number n such that the nth term of the sequence is greater than big M. In other words, no matter how high we set the bar, we can always find a term that manages to jump above it. On the other hand, a sequence is unbounded below if, for any little m we choose, no matter how small, we can find natural number n such that the nth term of the sequence is less than little m. In other words, no matter how low we set the bar, we can always find a term that manages to crawl under it, like some kind of infinite limbo master. Now, if you think about it, a sequence could easily be both bounded above and bounded below. If this is the case, we say that the sequence is bounded. No other words to detail it, just bounded. To show that a sequence is bounded, we would need to find two separate bounds: an upper bound to contain the terms of the sequence on top, and a lower bound to contain the terms of the sequence on bottom. On the other hand, if a sequence is either unbounded above or unbounded below, we often say that the function is unbounded in general. Again, it'll come in handy for a sequence to be bounded in various ways, and we'll see why that is quite shortly. Okay, now it's time to touch on one of the most important notions for sequences in real analysis. This time, the operative question is, where is our sequence going? Is it approaching some number, getting closer and closer to it? Or is it just going on forever to infinity? Maybe it's not doing either, and it's just jumping around, without any real sense of where it's going to end. What we want to know is called the convergence of the sequence. This is where the material from the last lecture will come in really handy. We say that a sequence converges to some number L if for every epsilon greater than 0, there is some natural number big N, such that whenever little n is greater than that big N, the distance between a sub little n and L is less than epsilon. That is, a sub little n is in the epsilon neighborhood of L. Now that's a mathematical mouthful, but the underlying concept isn't actually all that bad. What's really going on here is that if a sequence converges to a number L, then that means we're saying that the terms of that sequence approach L, and that we can get as close as we want to L. We just need to find the term after which everything in the sequence is less than some specified distance away from L, as in within some precision. We have a special term for the number L that our sequence approaches. We call it the limit of the sequence. Limits are an important concept when you begin to study calculus. In fact, they're arguably the foundation upon which the entirety of calculus is built. So we'll be talking about them a lot for the rest of this lecture. Now, of course, the easiest way for a sequence to have a limit is for the sequence to be constant after some point. For instance, consider the sequence 1, 4, 6, 4, 1, 0, 0, 0, and so on, in which every term after the fifth term is 0. As you can easily verify, the limit of this sequence will be 0. In a way, when we're talking about the convergence of sequences, sequences that are constant after a certain point are pretty trivial, so we won't really be considering them from here on out. But non-constant sequences can converge to a limit as well. If you remember our discussion from last class, you might have figured out what kind of point such a limit would be, based on the definition. Any ideas? It turns out that the limit of our sequence would be a cluster point. Remember that a cluster point of a set is a point around which any non-zero epsilon neighborhood contains at least one other point of the set, and therefore, as we proved, an infinite number of points of the set. Well, in this case, what we're saying is that if the sequence converges to that limit, then for any non-zero epsilon after some point in the sequence, all the terms will be within the epsilon neighborhood of the point. In fact, because of this fact, cluster points are also often called limit points. Now, pay close attention to the definition we used. Notice that I didn't just say that we get closer and closer to our limit, but instead I said we can get as close as we want to our limit. This is an incredibly important distinction. For instance, consider the sequence 0.1, 0.01, 0.001, 0.0001, and so on. These numbers are obviously getting closer and closer to 0. But if you think about it, they're also getting closer and closer to -5. You can easily check that the distance between these numbers and -5 is in fact getting smaller and smaller the further you go in the sequence. So then what is it that apparently makes 0 so special? The fact that you can get as close as you want, what some mathematicians call arbitrarily close to 0. You just need to pick an epsilon, say 1/1,000,000th, and I'll tell you at which point the distance from those points to our limit will be less than that epsilon. In this case, it's n equals 6. After the sixth term, every single term of this sequence is less than 1/1,000,000th away from 0. So we'd say that 0 is the limit of the sequence. This is one of those situations in which it pays off to be precise, almost to the point of being pedantic, so we know exactly what number our sequence will be converging to. On the other side of the coin, we might find a sequence that doesn't settle down and converge to a limit. Whenever this happens, instead we say that the sequence diverges. There's a couple of different ways that a sequence might diverge. Perhaps most obviously, the sequence could get larger and larger without bound, like the sequence 1, 2, 4, 8, 16, etc. Or perhaps smaller and smaller without bound, like the sequence -3, -5, -7, -9, -11, and so on. Or perhaps the numbers oscillate, such as the sequence 1, -1, 1, -1, 1, -1, forever switching back and forth between 1 and -1. This sequence doesn't converge. Try to use the definition of convergence to see why. But basically, if the sequence doesn't have a limit, we say it diverges. So the natural question to ask is, how can we tell if a sequence will converge or not? Well, we can now lay out at least one condition under which a sequence will have a limit based on our definitions we've just established. Here it is. Sequences that are both monotonic and bounded in the right direction must converge to a number. Specifically, a sequence that is increasing and bounded above will converge. We know that the terms of the sequence get larger and larger, but they can't pass some threshold we find. So the limit of the sequence must be at most that particular upper bound. In fact, if we were to consider all the terms of a convergent monotonic sequence as a set, then we can actually characterize exactly what the limit of our sequence will be. Any guesses? The limit would have to be the supremum of the set. The numbers would be getting closer and closer to that supremum, but might never touch it. So the supremum of our set would be greater than or equal to every term of that sequence. If we instead compared the terms of our sequence with another upper bound of the set, then the distance between the terms and our upper bound would never be less than the distance between the supremum and our upper bound. The only number we can get arbitrarily close to is the supremum. Of course, if we say that increasing sequences that are bounded above are convergent, it should make sense that we can also have convergent sequences in the other direction. That is, a sequence that is decreasing and bounded below will also converge. And as a parallel to what we just discussed, if we look at all the terms of the sequence as a set, then the limit of our sequence would have to be, you guessed it, the infimum of the set. So in general, the limit of a monotonic bounded sequence will be the supremum or infimum of the set. Okay, you know what? This is going to get somewhat off topic, but I feel like it needs to be said. We saw earlier how we can use the word monotonic to describe the dual nature of the concepts of increasing and decreasing. In fact, a lot of similarly related concepts exist in math. And in a lot of cases, there's a single word that encompasses both of the concepts, so they can be referred to at once without needing to refer to the particular direction in mind. Like how the word extremum encompasses the concepts of both maximum and minimum. But one thing I've noticed is that no such term seems to exist that encompasses the concepts of both the supremum and the infimum. This vexes me. I feel like by now a word should exist that covers both of these possibilities. So, I'm going to invent one. Right here, right now, for this course on YouTube, for Project Polymath, and wherever else you might see it in the future. Ready for this? The word I'm going to use is ultimum. Ultimum is a Latin word that means furthest, so I think it fits. It's the furthest down the upper bound can go, or the furthest up the lower bound can go. Or you can think of it as it's the furthest the set can go in either direction, even though it may never reach the ultimum. To get further into the linguistics of it, it's a second declension neuter noun in Latin, just like maximum, minimum, extremum, supremum, and infimum. So it's consistent with the existing terminology. By the way, this means that the plural form, say for when we want to discuss more than one ultimum, would be ultima. So when one of these days you see real analysis books getting more general and mentioning the ultimum of a set of numbers, or the ultimum property of the reals, you know you heard it first right here. Anyway, now back to our regularly scheduled sequences. So this whole business about finding limits is just fine, until we consider one crucial fact. Suppose we're looking at sequences of rational numbers. Then we can create all sorts of sequences, but we'll run into a particular problem. Some sequences, in fact a good number of them, will converge to irrational numbers. In fact, Having just talked about monotonic bounded sequences, we can use one of these as an example. Consider the following sequence: 3, 3.1, 3.14, 3.141, 3.1415, 3.14159, and so on. I won't list all the terms of the sequence. As you can see, this sequence is monotonic and bounded above, so it should converge to the supremum of the set of all the values of the sequence. You've probably noticed already that this sequence is building the digits of pi one by one. Since each term is a terminating decimal, it's rational. But pi itself, as I'm sure you know, is irrational. So if we were just looking at the rational numbers, there would be no rational number that this sequence converges to. As we discussed a couple of lectures ago, a set of rational numbers may have a supremum, or really an ultimum in general, that isn't in itself a natural number. So we wouldn't be able to say that the sequence converges in the rationals. But what if we considered this exact same sequence in the real numbers? Well, because of the supremum property we discussed earlier, or in general my newly named ultimum property, the supremum of a set of real numbers will always be a real number itself. So this exact same sequence would in fact converge to the number pi if we consider it a sequence of real numbers. This leads us to one more important property of the real numbers. First, we need to define the notion of a Cauchy sequence, named for the French mathematician Augustin-Louis Cauchy, who was an early pioneer of real analysis, and started to give calculus a firm foundation after its somewhat more rocky beginnings. A Cauchy sequence is one for which, given any positive real number epsilon, we can find a natural number big N, such that whenever little m and little n are greater than big N, the distance between a sub little m and a sub little n is less than epsilon. Again, the formality of this may look scary, but the concept is quite simple. Basically, a Cauchy sequence is one in which the terms get close to each other. We need to find an epsilon such that after some point, any two terms of the sequence are less than epsilon away from each other. So again, look at the sequence from earlier that was spelling out the digits of pi. Is this sequence Cauchy? Absolutely. For any epsilon, no matter how small, we just need to go out to a far enough decimal place, after which point all the successive approximations of pi will be much less than epsilon away from each other. With this notion in hand, it's time to reveal one more great thing about the real numbers. Every Cauchy sequence of real numbers is guaranteed to be convergent, to a real number, of course. This works even if we don't have one of our nice monotonic bounded sequences. All that matters is that the terms get close enough to each other, and we can know for sure that they'll get close to some real number. We have a special term for this milestone property of the real numbers. We say that a set is complete if, in that set, every Cauchy sequence converges to something within that set. So we would say that the reals are complete. This is a big deal, because it guarantees that just about any time we come up with a sequence that looks like it should converge, it does. In fact, in the real numbers, a sequence is convergent if and only if it's Cauchy. So a common way to show that a sequence diverges in the real numbers is to show that it's not Cauchy. A great example is the oscillating sequence from earlier: 1, -1, 1, -1, and so on. All we need to show that the sequence is not convergent is to show that it's not Cauchy. Given any epsilon less than 1, the difference between any two successive terms will be greater than epsilon. So there's no way the sequence can be Cauchy. Thus, it's not convergent either. But the interesting thing is that the completeness of the real numbers tells us something about the rational numbers. We say that a set A is dense in a set B if every element of B is either an element of A or a limit point of A. So we can see that the rational numbers are dense in the real numbers. We take advantage of this fact every time we use an infinite string of decimal numbers to represent a real, possibly irrational number, just like we did before with pi. Since these sequences we get by successive approximations are Cauchy, they're guaranteed to converge to a real number. And since Q is dense in R, every real number can be approximated in such a way. In fact, since R contains all the limits of Cauchy sequences from Q, we would say that the real numbers are the completion of the rational numbers. So that about wraps it up for our short foray into real analysis. But there's one more question that needs to be answered. Remember that the title of this lecture is Sequences and Functions. Well, we've spent plenty of time talking about sequences. But what does any of this have to do with functions? Well, the rather simple answer is that many of these concepts can be generalized to apply to functions. Remember that a sequence is itself a kind of function, one for which the domain is the natural numbers. But in calculus, we're most often concerned with functions for which both the domain and the codomain are the real numbers. Functions that, when graphed, do in fact connect the dots in ways that sequences never could. Even so, many of the concepts we just discussed transfer over just fine. Functions can be monotonic. They can be increasing and they can be decreasing. They can be bounded, above, below, or both, or they can be unbounded. And they can have limits. If we consider a function f of x from R to R, or at least from some subset of R to R, then we can easily talk about the limit of the function as x approaches infinity, which we often write like this. But the nice thing about functions of real numbers is that we can also talk about the limit of a function as its input approaches any real number. For instance, consider the function f of x equals x squared minus 9 divided by x minus 3. Note that we can't evaluate this function directly at x equals 3, because doing so would yield 0 over 0, which creates all sorts of problems. But we can plug in numbers that are really close to 3. F of 2.9 equals 5.9. F of 2.99 equals 5.99. F of 2.999 equals 5.999, and so on. Or we could go from the other direction. F of 3.1 equals 6.1. F of 3.01 equals 6.01. F of 3.001 equals 6.001, and so on. So as you can see, the closer x gets to 3 from either side, the closer f of x gets to 6. So we would say that the limit of f of x as x goes to 3 is 6. This concept is often one of the first things you learn in calculus. So if you haven't taken calculus yet, you can now consider yourself prepared. But even if you have learned calculus already, either way, now you should have a sense of why we're allowed to do something like this. The fact that the reals are complete allows us to approach these numbers without having to worry about whether we'll be approaching a number that should be there but somehow isn't. In essence, knowing a few things about the real numbers gives us an idea of why calculus works. That's it for this lecture. In our next lecture, we'll be moving away from looking at just the real numbers and instead enter the realm of abstract algebra, in which we'll discover some deep relationships between all sorts of sets of numbers. And all that will start with a very simple but beautiful concept: groups. See you next time.